Hello, this video presents our work, Cooperative Grasping for Collective Object Transport in Constrained Environments, submitted to the Robotics and Automation letters. In this work, we address the challenge of selecting optimal grasp configurations for two robots to collaborate on transporting objects in constrained environments. These configurations must ensure a secure hold and facilitate a feasible transport trajectory through a narrow corridor. To address this challenge, we propose a learning-based framework that identifies feasible grasp configurations for two robots. This framework is especially designed to handle the geometric intricacies of both the object and the environment. The object to be transported is equipped with stable grasp points around its perimeter. These positions are selected to ensure that a gripper can securely attach and manipulate the object. We model the object from a top-down perspective, placed on a table, and for each grasp point, sample feasible mobile base positions based on the robot's reach and collision constraints. This position represents where a robot can safely position itself to grasp the object. By pairing each grasp point with every base position, we generate a set of possible grasp configurations, each defining how and where a robot can hold the object securely. Given the set of grasp configurations, Robot 1 selects a grasp configuration G-center and Robot 2 selects a complementary configuration G-context. Forming such a pair significantly increases the likelihood of finding a feasible trajectory for the robots to transport the object through a narrow corridor. Once both robots adopt their selected grasp configurations, they can approach and securely attach to the object to finally execute the trajectories. To identify viable grasp configurations for object transport, we propose a conditional embedding model. Given the object geometry and environment map, two embedding networks, center and context, encode all candidate configurations conditioned on the scene. The center network generates an embedding for each possible configuration that could be selected by Robot 1, while the context network produces embeddings for all potential complementary configurations for Robot 2. The dot product of these embeddings yields an affinity matrix that captures the feasibility and synergy of all possible configuration pairs. The optimal pair is found by selecting the index with the highest affinity score or by retrieving the top K pairs for further evaluation. We conducted a series of pipe-bullet experiments using objects of various shapes and different environment setups to demonstrate the generalizability of the conditional embedding model in selecting grasp configuration that enable collective object transport through narrow passages. Additionally, we evaluated the conditional embedding model in physical experiments using two mobile manipulators tasked to decide the grasp configurations and compute the trajectories to execute the object transport. We evaluated our framework using two objects, a long bar and an L-shaped object. For each, we generated possible grasp configurations, and the conditional embedding model selects the optimal pair for cooperative manipulation. In the first scenario, the robots are tasked with transporting a long bar from one room to another through a narrow passage. This experiment demonstrates how our method enables both robots to select optimal grasp configurations and plan collision-free trajectories, allowing them to efficiently move the bar through the constrained space. In the second scenario, we increase complexity by tasking the robots with transporting an L-shaped object, whose geometry poses additional challenges for grasp selection and trajectory planning. Building on the previous scenario, this experiment highlights our method's ability to handle objects of more complex shapes, while still selecting optimal grasp configurations and generating collision-free trajectories. Both scenarios use two mobile manipulators, each composed of a Clearpath Dingo mobile base and a 6 degrees of freedom Kinova robotic arm. Thank you for your attention.